Hi, everyone. We've set up this Being an Engineer podcast as an industry knowledge repository, if you will. We hope it'll be a tool where engineers can learn about and connect with other companies, technologies, people, resources, and opportunities. So make some connections and enjoy the show.
Hello and welcome to another wonderful episode of the Being an Engineer podcast. Today we are privileged to speak with Bradley Rothenberg, who is the founder and CEO of nTopology, a company pioneering next-generation engineering software for advanced manufacturing. Launched in 2015, nTopology enables engineers to create complex, optimized geometries, primarily for sectors like aerospace, automotive, and medical devices, optimized for additive manufacturing. With a background in architecture from Pratt Institute, Bradley brings a unique perspective to computational design, bridging the gap between form and functionality in additive manufacturing. Bradley, thank you so much for joining us today.
Yeah, thanks so much for having me on that podcast. It's awesome to be here.
So I should have asked you before we started recording, but do you typically refer to your company as nTopology or just nTop?
So it's actually funny. I started the company as nTopology. Literally, the meaning means like N for any, and then topology, which is like the mathematical structure of shape. And it was really because I wanted to make software that could allow you to make any shape. I didn't want shapes to be a bottleneck. And actually, about a year and a half ago, we acquired the 4-letter domain ntop.com after several years of negotiation. And once we acquired that domain, we shortened the name to nTop. And I kind of like to say we lightweighted our name, chopping off some letters. Now we officially go by nTop, but nTop is short for nTopology, so I'm okay. Some of our social media handles are still nTopology.
Got it. Okay, great. That's good history. So you have a background in architecture. Tell us, how did you move from architecture to creating nTop?
So I actually think the origins of nTop go even before architecture school, when I was in high school and obsessed with our CAD program. And so I had this CAD teacher from freshman year to senior year of high school that was teaching, we were in Fairfield County in Connecticut, which is also the home of GE. And so GE would like sponsor all the local schools. And I went to public school, but we had this amazing CAD program where we were learning computer-aided design, and we had a 2D pen plotter. And I would always finish the CAD assignments early. And I taught myself how to program through writing add-ons to AutoCAD at the time and basically hacking the pen plotter to do all sorts of crazy things. And so, when I went to college, I thought the architects were using more interesting software than the engineers in school. So I decided to study architecture. And it was in 2005 when I was at Pratt that I was working in the lab, the digital manufacturing lab, and the professor, one of the heads of the lab, was like, "Hey, we just got this new machine. It's called a 3D printer. It can consume a 3D file and it prints it in 3D. And so who wants to manage it during the summer?" And I immediately raised my hand because I was like, this sounds like the coolest thing on the planet. I was really obsessed with laser cutters and programming them to make certain shapes. And when the 3D printer came, for me, that was kind of the first connection between a lot of the programming I was doing to write plugins and add-ons to CAD systems and actually manufacturing. And to me, the 3D printer was like this game-changing step where it's like, okay, you can model something in 3D. And it was the first true way of manufacturing a 3D model that was created digitally. And so I very quickly found out that the way that the current tools represented 3D shapes and 3D geometries was a bottleneck and was holding me personally back from making these type of shapes and producing these shapes. And, it's funny because computational design was a term that we used in architecture school. And we talk about computational design a lot now with nTop, which is literally capturing the requirements for an engineering problem into a set of computer algorithms so we can use computers to actually compute and produce shapes. And I've always been obsessed with how we can use computers to help us create new shapes and create new products. And so to me, architecture school was kind of one step in that direction, where I was like, okay, we have these computers and now computers that can print and produce 3D products. And there's a gigantic bottleneck which was the kind of state of the art CAD tools were developed on top of technology that was, created in the late 70s, early 80s, that was still kind of built on the fundamentals of drawing and drafting. And so instead of capturing requirements in a set of algorithms, the CAD tools, which are phenomenal, were built to kind of capture drawing operations in a set of sequential operations. And so whenever you're producing something in a CAD system, you're essentially producing a set of drawing operations. You make a sketch in 2D, you extrude that sketch, you have multiple bodies, you're joining bodies and combining bodies, you're clicking on edges, you're adding fillets. And those are essentially, to me, it's kind of the same thing as drawing and drafting. It's just using the computer to draw and draft. And what I was really interested in is, we have all of this amazing amounts of compute at our fingertips. We have GPUs, we have parallel compute. And, how could we use that compute to actually create the 3D shapes for us? And in order to do that, we need to capture those requirements that drive the shape in a set of algorithms. And that's kind of why I created nTop, which is to better use computers to help us create new products.
Give us a tactical example of how nTop differs from, say, SolidWorks or Creo or any of the other more traditional CAD programs out there.
Yeah. So, I think, if you look at the work that Siemens Energy is doing in our software, they're designing, so the products that Siemens Energy makes are like the biggest jet engines on the planet. Like when you fly, you see these gigantic jet engines. Well, they make jet engines that are like 10 times the size of them. They're like 18 feet high, the size of school buses, and they power cities. In fact, I think there's like 4 of them, 14 blocks north of me in New York City that's providing the power to my apartment. And these turbine engines are running off of, fossil fuels today. And one of the goals is to convert those to hydrogen power. And hydrogen power burns much hotter, and you have to control the flame. And it's a much harder, it produces a lot more heat. And so in order to redesign some of the burner components and the heat exchangers, these are extremely complex engineering problems where they need to model these shapes that basically pull heat out of one fluid and transfer the heat into another fluid. And in order to do that, they create these, hundreds of thousands of tubes that kind of weave around in and out of each other. And one set of tubes has one fluid and another set of tubes has another fluid, and there's metal in between them. And the goal is to transfer as much heat from one material to the other with as little pressure drop, because you have to have a pump to pump the fluids through, right? And so this is an engineering problem that you could, if you were to do this in a traditional tool like a SolidWorks or NX or CATIA, you would sit there and draw kind of all of these tubes, or you might create one tube and array them in a way, but you create a set of manual operations to build up these tubes. And you'd have kind of one version of the design that you would then run through simulation, maybe some CFD, you'd run conjugate heat transfer and solve this kind of coupled thermal fluidic problem to understand the pressure drop and the temperature drop. And once you get your result, you go back to the drawing board and you're like, wait a second, there's too much pressure drop. And so you have to start over again and kind of redraw all of those tubes or try and stretch them out a little bit. And, each iteration essentially takes a set amount of time, and each step you're making a better heat exchanger. And I think if you take a step back, engineering is like a problem solving process, right? And so when you're engineering a new product, you make a design, you test it, you learn something, and then you go back to the drawing board and you make it better. In nTop, you're capturing those requirements in a set of building blocks. And so we have this concept of building blocks in nTop. And so you might have a block in nTop that can take a 3D space and divide it up into multiple domains. And you might have some parameters for those domains, like number of tubes, the periodicity of a sine wave maybe, or or a curve going through the tube, or maybe you have some shells and some fins going through, and you have the definition of that 3D shape in what's called a block, and there's a set of parameters going into that block. And then you might have some parameters for where some inlets go. You might have 2 inlets for the hot fluid, 2 inlets for the cold fluid, and then 2 outlets for the hot fluid, 2 outlets for the cold fluid. And you might want to change that to 3 inlets or 4 inlets or 5 inlets. And so you create this, let's say, like very parametric model where all of the parameters or these variables going into the model kind of control or create output shapes. And the model is very robust to changing those parameters. So if you wanted to see, what happens if I have 20,000 tubes instead of 10,000 tubes, that's a parameter that you change and the model just updates instantly. And then that model is also tied directly to the fluid simulation, so you can see and measure the fitness of each design point. And so, if I use a more simple example, maybe it's even easier. Like if you think about an airfoil, this is like the most simple thing, a wing, right? And a wing, NACA airfoil, you have parameterized by its thickness and camber equations. And so in an nTop model, you can capture, the equations for thickness, the equations for camber, and produce the output wing shape. And so, in a CAD system, you might draw the curve for that wing, and that represents one curve. But by capturing like the entire requirements and the engineering problem in the nTop model, you don't just capture kind of one version of that wing or one version of that heat exchanger. You capture all possible variations of that heat exchanger or all possible variations of that wing so that, you could run a big design study automatically using computers to try and figure out what's the best performing wing or what's the best performing heat exchanger, right? Because each design point or each set of parameters produces a design, and each design has some fitness. Is it better or worse? Is it better to have 20,000 tubes? Is it better to have 10,000 tubes? Is it better to use an airfoil with a lot of camber, or is it better to use a flat airfoil, right? And so the power of these computational models is that you can iterate and make changes very, very quickly in real time. And instead of being limited by the amount of time it takes you to like manually redraw the shape, you're now limited by how fast your computer could compute the shape. And so we're trying to basically speed up the development time in order of magnitude faster than the legacy tools. Just as the legacy tools sped up the iteration time in order of magnitude faster than like paper drawing and drafting.
What kind of computer do you need to run nTop effectively? Do you have to use a really high-end computer, or is some of the computing done in the cloud and it doesn't matter that much how high performance your machine is?
So I run nTop on my laptop, and also I have a desktop at my desk that I sometimes remote into, or I'll work off of that. And like my desktop has a really fast GPU. It has like the newest Ada 6000 in it. It has a Threadripper and like 256 gigabytes of RAM. And my laptop is kind of just like a 2-year-old normal laptop. And, nTop runs really well on both of them. Obviously, it runs a lot faster on the computer with multiple cores of CPU and the faster GPU.
Yeah.
But what's interesting is, these models in nTop are extremely lightweight. Like we have this like fully parametric model of a jet engine that's like a megabyte in size, or the heat exchanger.
That's crazy.
Yeah, it's totally insane. Like a model like that as a CAD model could be
Gigabytes.
like 600 or gigabytes. A heat exchanger that could be like 8 gigabytes in nTop could be a megabyte. And the reason for that is our core modeling technology is based on what's called signed distance fields, or implicitly defined signed distance fields. And so instead of having to like store all of this surface data in memory and calculate all these intersections of surfaces, we basically store a really complex mathematical equation. And our software is really good at compiling that equation into machine code so that the computer could render and compute things about those shapes. And so
Interesting.
that's what makes nTop different and special and so fast is the core technology that we're built on.
Have you ever considered or been approached about licensing that modeling technology to other CAD platforms? I bet that would be a huge advantage for like if SolidWorks could all of a sudden deliver files that were 1 megabyte in size.
Oh, 100%. We actually have a product for that also called nTop Core. And so nTop Core is a library that we've released for partners to basically read and write nTop data directly. And we haven't done it yet, but it's something we're considering, which is opening up more of the modeling API into nTop so that partners can start to build more complex applications on top of nTop Core. Like today, the most common use case of nTop Core today is for Materialize with Magix incorporated nTop Core into their software so that they could consume an nTop implicit and then slice it for 3D printing in version 28.
Okay.
Autodesk Fusion also we just released a plugin together with Autodesk to read nTop implicits into Fusion for the same purpose, build simulation and build processing for 3D printing. Soon we'll have CAM and other types of CAD-like operations.
What's the modeling like in nTop? Is it similar at all to traditional CAD programs, or is it completely different?
So it's definitely not similar. The way I like to think about it is you're constructing or building a set of relationships that produce the geometry rather than defining the geometry itself. So like when I use the term implicit, it's like instead of defining and drawing a set of edges, you're kind of drawing a set of primitive shapes and the edges happen at the intersections. And you could add fillets and rounds at those intersections. But the modeling itself is like, it's different. Like if you've used CAD for 25 years, you're probably going to open up nTop and be like, okay, this is really hard. But, for on the flip side, we had a high school intern with us all summer and he's used Fusion before in his first robotics club. But, he picked up nTop in 2 days and he modeled and 3D printed completely in nTop, a tricopter drone that he 3D printed and assembled, and it didn't quite take off yet, but this was in 6 weeks of an internship. And I think if he had 8 weeks, he would get it to take off. And that actually wasn't because of the mechanical system. It was because of the electronics, and getting those to work was more complicated.
That is super impressive. Wow. So it's not really like a traditional modeling system. It's more define the constraints and let the software build the model.
Yeah, or set up the set of relationships.
Okay.
In nTop.
Okay. And what different physics does this work with? I mean, there's like loads, vibration, heat, fluid. Like what are the core physics that your engine works with?
So internally, we have our own linear static stress solver, vibration, and thermal. And those are all like using traditional finite elements. So the nTop model, you take the nTop model, you mesh it, and then you create a volumetric mesh automatically in nTop, and then set up like a traditional finite element analysis. We recently launched a few integrations directly from nTop where you could run meshless simulation. So instead of having to mesh the implicit itself is sent to the solver, and then the solver does some interesting things with that, like puts points inside of it or surrounds it with a grid and can solve the physics over that type of data structure. And we did that with a company called Intact Solutions for their stress solver. And then we also did that with a company out of Germany called Cloud Fluid for their computational fluid dynamics, their lattice Boltzmann fluid solver. And then you can also do pre-processing to set up models for other tools as well. And so, the integrations, like one of the big steps that has kind of moved the needle for nTop in the last year to 2 years compared to when we launched 5 years ago is how integrated nTop has become into our customers' digital thread. Because like we're in around 400 accounts right now. And our customers use our software kind of next to or with all of the mainstream CAD systems from CATIA to NX to Creo, SolidWorks. And they're using nTop models and solving the physics inside of nTop for the kind of design experimentation loop, but then also in like Star CCM, in Fluent. On the fluid side, they're using us with LS Dyna on the nonlinear side. And so I think engineering software, like it's not really just like a winner take all kind of market. Like our customers are using the best tools for the job always. And, the way that nTop implicits can integrate into those tools has been really critical to us, to our customers really seeing the value of what being able to iterate like an order of magnitude faster can do for them.
That's great. I'm going to take a very short break here and share with the listeners that the Being an Engineer podcast is brought to you by Pipeline Design and Engineering, where we don't design pipelines, but we do help companies develop advanced manufacturing processes, automated machines, and custom fixtures complemented with product design and R&D services. Learn more at teampipeline.us. The podcast is also sponsored by The Wave, an online platform of free tools, education, and community for engineers. Learn more at thewave.engineer. And we are privileged to be speaking with Bradley Rothenberg today. Talk a little bit about the handoff between nTop and other CAD programs. So, for example, if I'm using SolidWorks for most of my CAD modeling, and I'm using nTop, how do those two applications shake hands? How do they trade files between each other?
So let's say you're working on an assembly in SolidWorks. Maybe you're making maybe you're like our customer Ocado and you're designing a factory robot, and you have the kind of assembly that you're doing your kind of assembly itself in SolidWorks, and you might want to do some optimization on some of the parts. So you might do some like the most common application of nTop today is, detailed level part design for 3D printed parts. And so, you might have you build your assembly and kind of set up, okay, here's where I want a motor to sit. Here's where I have a gearbox. Here's where I have some tubes coming together. And in SolidWorks, you might have a region that you want to create a part in, and you don't necessarily know what you want that part to look like, but it has to fit within a certain area, and you have kind of keep out zones and stuff like that. So you might export that as a step file or save the SolidWorks part file for that component, and you'll import that into nTop. You'll set up your problem in nTop, set up your loads, your boundary conditions, and you'll run your problem in nTop and produce a component or a part. And that part you could then export as a step file and bring that back into SolidWorks as part of the assembly.
Got it.
Now, you might also do the analysis from the nTop model itself as well. Now, our customers that are kind of using like PLM environment, like Windchill or Teamcenter next to CATIA or next to NX, they'll manage that nTop file directly in the PLM system. And for each change that happens upstream of nTop, that will kind of automatically get fed into nTop, and that can be updated with the design process. We also have a newer set of applications, not at the detailed part design level, but much earlier in the process, in the kind of low fidelity concept design, where customers are starting in nTop and creating a model. It's more like a low fidelity systems model in nTop, where they can iterate really fast. And the things I'm thinking of are like, drones, unmanned vehicles, smaller robots and stuff like that, where a model is built in nTop that could take in some of the initial requirements. Maybe you have some payloads or gas tanks and you have an engine, and you want to see what happens if I change where the engine is, what happens if I move the wings around. And very quickly you can iterate through like thousands of different variations of a kind of low fidelity concept model. Once that model is honed in and meets the requirements that you want, you can then make it a step file and bring that step file into SolidWorks or NX or CATIA and have that as a starting point to then do all of your downstream detailed level design from. And so that's kind of a newer area, but like our bread and butter has been in the detailed part design.
Okay. And you mentioned that the biggest use case for nTop right now is in additive manufacturing, 3D printed parts. And I'm assuming that's because I'm no expert at all when it comes to nTop. I've seen parts that have been made there, and they seem to have this very organic shape and structure to them. Almost, I feel like the word anatomical almost applies. It's almost like this like network of vasculature, different veins and lofted surfaces weaving throughout. And so I'm guessing the reason 3D printing has been found to be such a successful application of the technology is because you can make these crazy shapes in 3D printing that you just can't make if you're injection molding something or machining something. Is that a true statement?
Yeah, I mean, I think that's, for those type of design problems, nTop is kind of the only technology that can produce those type of shapes in a robust, fast, and easy way. And so, early on in our deployment, we saw a ton of those type of components and a ton of like heat exchangers anywhere where, if you look at these type of models and think about having to like draw them in a CAD system, it would drive you kind of nuts.
Yeah.
But
there's no way.
Actually, yeah, there's no way. Like a heat exchanger with, hundreds of thousands of tubes, or trying to optimize where the composite, the orientation of composites through an automated fiber placement machine or an automated tape layout machine. And so things like that, where you're dealing with like very complex geometries, nTop core technology is really, really good at solving.
So if I understand correctly, we look at an example where nTop is solving a structural problem, you've got some part that is bearing loads on let's say the top and the bottom. And so you apply these boundary conditions within nTop. You've got loads here, you've got a ground there. nTop starts doing the FEA, the solving, and it identifies areas in this block of material, this theoretical block of material with which you start, that just aren't needed for the structural support of that component. And so it strips those areas away and kind of just leaves the areas that are required to support those loads, which is why at least these models can end up looking like, I'm using the word anatomical. I don't know. I've always had that thought that they look like anatomical models because they're so organic in their shape. Is that more or less how it's working?
I think that's yes, for when you run the kind of density-based topology optimization.
Okay.
And so there's an algorithm that's in nTop called density-based topology optimization. And basically what you're doing there is you're taking like a block of material, applying some loads to that block of material, and the algorithm is removing material where it's not needed. So essentially what you get is like a kind of a tracing of where the load paths are.
Right.
Through a part.
Yeah.
And so that's a fairly common use case of nTop, and our implicit modeling tech is really good for that. But you can also build up models that you kind of build in. Like one of the things with those is, if you can build this freeform shape, can you actually manufacture it with the traditional manufacturing process, not just 3D printing? And so what we also, you can build in some constraints to the topology optimization so that it's, you make sure that if you're machining it, the tool can always like get at the part in each direction. But you could also build up a model from the beginning that takes into account the manufacturing constraints. Like if you're building an injection molded component, that injection molded component can, you can make sure all the walls are always the same thickness and you're not changing cross-sectional area too much. And you have a set of ribs that are in certain areas and you have a set of stiffeners. And you might have an A side surface that you want to maintain, but the B side surface doesn't matter, but you just can't hit other certain regions. And so you can build those in to a model that's not necessarily just running a traditional topology optimized model. And so I would call that kind of like a parametric model in
Yeah.
nTop that's very robust and very quick to make changes.
That's very cool. I didn't realize that it had that capability. I thought it was always this like very organic shape that got exported. So does that infer then that you can set up your model so that the export, if you need to bring it into another platform like SolidWorks or Creo or whatever, you can export models that have basically flat faces on them so that you can do additional modeling operations if you need to on nice, clean, flat faces.
You can, absolutely. And some of our like mesh to step filing is getting really good at identifying those flat faces. But my question always is like, what additional modeling do you want to do in the CAD system? Like, why would you not do that in nTop itself?
The example that came to mind was like draft on a part, and maybe you could just add the draft in nTop, and you don't even have to worry about that as a post operation.
Yeah, draft is a block in nTop that you can just like apply. You have your plane that you want to draft from.
Okay.
You have your select your server, and it's actually it's pretty automatic. So that's kind of
That's awesome.
And the nice aspect of that. But I think there's a lot of people who use CAD historically have certain things that they know work, and they have certain ways of like kind of hacking the CAD model to get what they want. And so a lot of times when I'm talking to customers, their first thought is like, okay, I want to bring this model back into CAD so I could do add draft, or I can add a hole here. And they don't realize that actually adding that still, while it's an implicit, might actually be faster and better.
Yeah.
And if you're adding draft, then like, you can do the analysis on the drafted part. You're not doing that as like a post-processing operation.
If you wanted to, are there ways that you can add discrete features? Like if I wanted to add a hole that was 0.782 inches in diameter and 0.3325 inches deep, is there a way to do that?
Oh, absolutely. I mean, everything in the model is defined through a set of parameters. So you can make a cutting tool that has those parameters and cut that out from your part.
Very
and
cool.
So,
okay.
Yeah, like all of those type of things you could do in traditional mechanical parts. Like when you're making a mechanical part, you can set that up. But the cool thing is that hole that's 0.332 inches with, plus or minus whatever tolerance you define, if you run the analysis and realize, wait a second, there's too much load at the bolted connection there, maybe you want to make a change and try a different size hole. You can just update that hole and the whole system will just update.
Right.
Similar to a parametric model. But a lot of times when you build a parametric model in a CAD system, you make an update and the model won't update, or it takes a long time to update. In nTop, that updating is like instant.
I feel like FEA is typically considered a separate process than CAD modeling, right? We might create our model in CAD, and then maybe you've got SolidWorks simulation, so you're at least in the same environment, or maybe you don't have that and you export it and run something in ANSYS, but it's like a separate operation. I get the sense that in nTop, it's not really a separate operation to run the analyses. It's more of a baked in, like just part of the workflow. Is that the right way to think about it?
Yeah, I mean, I think of simulation, and this is like a lot of organizations are set up where they have two different teams. Like they have a drafting team of draftsmen and a team of analysts.
Yeah.
And so the way I think about simulation is it's just one step in the engineering problem that you need to solve. And you need that very tight digital thread or very tightly coupled simulation to the model. So like if I make it like, ideally, what I want in the model is I want to make a change and see, okay, what happens if I thicken these little ribs? Or what if I use, 5 degrees of draft instead of 6 degrees of draft? How does that impact the performance of my part?
Right.
And I'd love to just make that change and see it in real time. Now, we're not there yet because the physics still takes time to run, but I think we'll be there within the next 5 years or so. But I don't know if that, I know getting it in real time is going to be tricky, but I think getting it in real time and accurate is going to be tricky. At least being directionally accurate, I think at that stage of design is probably good enough. And then you can freeze the model and let it run. Like I have a model on my, or before our sound cut out, I have a model on my desktop machine that's running, and I'm using nTop Automate to run through 100 different design options where I'm just doing a parameter sweep on the wall thickness of an injection molded part. And I'm trying to understand for a customer of ours running one of their models where like, what's the impact of the wall thickness to the weight of the overall component and the max stress throughout the component, and trying to hone in on what the wall thickness is. So my computer is doing that work right now, and I'll get back and I'll go see that. It'll probably be done in a couple hours. And the thing that takes time there is meshing the geometry to prepare it for simulation. And it's automatic, but it's still, the computer has to crunch away and figure out all these little elements. And then it's solving the actual partial differential equations over each of those elements to understand where the stress is in the part. And so if we could speed that up and make it accurate, I think that's kind of, where I want to go with this. And I think we're close. And I don't think of the simulation as something separate that's just done to like validate the part. Like the simulation, it's a way of understanding the fitness of one version of the design. And in a world where you're constantly making changes and constantly updating your design to get the performance that you want out of it, each time you make a change, you should see, okay, is it getting better or worse?
Yeah, in your case, in nTop's case, the simulation directly leads to and is directly linked to the final geometry of your part. Whereas in traditional modeling, you model your part, with a rough engineering understanding of what it should look like and how big it should be, et cetera. But you're often not optimizing that part based on any sort of FEA. It's usually just kind of engineering judgment, unless it's some kind of truly structural critical part. And then, of course, you could get into FEA. So maybe an interesting question to ask would be, what kinds of operations or actions should you not do in nTop within the context of modeling and creating part geometries?
I think today, actually setting up assemblies in nTop is really not so easy to do. Like we don't have all the constraints and all that stuff. And then we don't have a good sketcher yet. So like actually, I still think it's too hard to like define the geometry itself. Like you could set like for certain models where you need to iterate fast or you need to reuse them a lot. So like heat exchangers are a good example where I do recommend like modeling the whole thing from the beginning in nTop. But if you're modeling like a simple bracket or like something a sheet metal part, like that's better for a CAD system. Like if you're doing, if you're drawing where the tubes should go in a part, maybe automated pipe routing makes sense for nTop. But if you're just like going and drawing some tubes, that doesn't make sense. And a lot of the mechanical design, probably like 80 or 90% of the mechanical design that's done today still makes sense for a CAD system. But there's certain examples like designing the bulkheads of an aircraft where it's like the detailed design, or kind of the high fidelity structural layout of where the bulkhead should go in an aircraft system, which are very good problems for nTop.
What are some questions that an engineer should ask him or herself when trying to determine whether nTop is the right solution for their particular design problem? So
I think the good types of questions to ask are like, is this the type of problem where if I spend a little bit more time up front defining the sets of relationships that go into this design, it will actually produce a better design longer term by exploring what those relationships do? Or like, is this the type of model that requires lots of different changes in the structure or the topology to find the right design? And those changes are hard in the CAD system. If I make a change in a CAD system, I have to wait 30 minutes every time I make a change for the model to update. And there's like a 50% chance that model will fail when it updates. That's probably a good problem for nTop. Is this something that has, hundreds of thousands of surfaces that are all repeated and they're all a little bit different, but they're kind of the same? That's probably a good problem for an implicitly defined sine distance field based model. But I think the main thing is like, through the design process, am I going to be making a lot of changes? And those changes are hard to do in a CAD system and very manual. That probably seems like a good problem for nTop.
Great.
For you to do an nTop.
Okay, great. Well, Bradley, I think we'll wrap things up here in just a second. Before we do, are there any other questions or topics that we should hit on that we haven't talked about yet?
I mean, I think we probably could talk for like the whole day on computational design in general, and like how you build these models, the type of models that you build. I mean, there's a lot of like images, and we're engineering, so it's good to kind of see things. And so there's a video on YouTube that we made recently called The Powers of nTop that we made with the launch of nTop 5. And I see nTop 5 as kind of opening up this new realm of problems that computational design can solve, because what we did is we re-architected our core model to be an order of magnitude more precise and an order of magnitude faster, so that we can be useful for much more ambitious, larger scale problems. And I think this video kind of demonstrates that with the kind of drone model, the concept design for a drone, and then an engine system as well. And there's other types of like GIFs and videos of these type of models that I think kind of demonstrate the power and robustness of these implicitly defined models. So you can like make changes really quickly and learn from those changes. And then I think that the following us on social media also is obviously where you can find us and see what we're up to.
Terrific. You're the CEO of the company, so you don't want every Tom, Dick, and Harry reaching out directly to you. But if people have legitimate causes to do so, what's the best way to get in touch with you, and also the best way to reach out and learn more in general about nTop?
Well, actually, you can reach out to me on LinkedIn via messages or shoot me an email, brad@ntop.com. It's easy. It's 4 letters. So it's just brad@ntop.com. And I'm pretty responsive as well. I'm on Instagram as well. If you send a DM, usually I'll get back to you. And, I mean, I think we're pretty like open. We're a new piece of technology. And one of the things that's really important for me is to spend as much time as possible with with people that are using our technology. And so I'm always on the road. And so hopefully we'll have some more kind of meetups as we're traveling again and visiting our customers across the world. And so the other place to go is ntop.com, and you can sign up for a demo. You can see our learning materials, our support pages. Something I just want to make sure the listeners know too is that, we're free for students to use. And so if you're a student, you can go to ntop.com, go to the EDU tab, and you can sign up to get nTop for free. And that's super important for us because that's where you learn new software, right? Like if you're working for Honeywell is not paying you to learn new tools. And so I think it's important to start with nTop in college.
Phenomenal. All right. Bradley, thank you so much for your time. Congratulations on starting nTop all those years ago and the success that you and your team have seen. And thank you for being on the podcast today.
Yeah, thanks so much for having me. And we'll talk soon.
I'm Aaron Moncur, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services, visit us at teampipeline.us. To join a vibrant community of engineers online, visit thewave.engineer. Thank you for listening.